Hi, Algebra 2. This is Unit 4, Lesson 13. This is our last lesson. It's been a very long chapter. There are lots of things that we learned. This last chapter is about compound interest. So in the world of investment and debt, interest is added onto a principal in what is known as compound interest. The percent rate is typically given on a yearly basis, but could be applied more than once a year. That is known as the compounding frequency. Let's look at a typical problem. Say a person invests $500 in an account that earns a nominal yearly interest rate of 4%. So I'm going to take that 500 and I'm going to times it by 1 plus the rate. 4% is 0.04. Okay, and I want to know what it's worth in 10 years, and I'm going to do that to the 10th power. So if I do that in my calculator, all right, 500 times 1.04, I'll just add those together, and I want that for 10 years to the 10th power. So that gives me $740.12. All right, not too bad. Although it was 10 years, so that's a long time. Now, if on the other hand, that interest was applied 4 times per year, known as quarterly compounding, why would it not make sense to multiply by 1.4 each quarter? The 1.04, this is a yearly, rate. I can't do that each quarter because then if I was doing that 4 times a year, if I took that yearly rate and I did it 4 times per year, the interest rate would be much more than 4%. So this is a yearly. You can't take the yearly and multiply it by 4 because then your interest is much more than 4%. Interest much more than 4%. All right. This is sort of taking us through what we're eventually going to do. If you were told that an investment earned 4% per year, how much would you assume was earned per quarter? Okay, so per quarter, there's 4 quarters in a year. So if I get 4% per year, and there are 4 quarters in a year, it probably would make sense in your head if I took that 4% and I divided by 4 and I got 1%. All right, so using that answer, let's calculate how much the investment would be worth after 10 years of quarterly compounding. Show your calculation. So I got 500, okay, 1 plus 0.01, because now I'm going to use this lower interest rate here, but I'm doing it 4 times a year for 10 years. Okay, so I'm taking a lower rate, 0.01, but I'm doing it 4 times a year for 10 years, and 4 times 10 is just 40. So 500 at that lower rate, but instead of doing it 10 times, I'm actually doing it 40 times because the interest is going to be compounded quarterly. So 500, look at the difference in the money here. 500 times 1.01 to the 40th power. And I get $744.43. Now you might not say, well, that's not really a huge difference. So 744 versus 740. Well, I'm only talking about compounding it quarterly, and I'm only talking about $500. If you're talking about thousands and thousands of dollars, it makes a huge difference. All right? Let's look at the next problem. So for a shorter compounding period, you get to apply the interest more often, but at a lower rate. So say I had $1,000 invested at a nominal 2% yearly rate, compounded monthly. So now this is monthly. Monthly is going to be 12 times per year. What would it be worth in 20 years? All right, so basically what I did before is I took that percent and I divided it by quarters, 4. If I took 2 and I divided it by 12, that gives me 0.1666. That's kind of ugly. So I'm just going to leave it as a fraction. So I'm going to take the 1,000, okay, which was my investment, times it by 1 plus, my interest rate is 0.02, but I'm going to divide it by 12 because I'm doing it quarterly, but then I'm going to multiply it by 12 times 20, all right, because I'm doing it monthly. So I'm going to take the actual rate, 0.02, I'm going to divide it by 12 because I'm doing it monthly, but then I multiply it, the exponent, the 20 years, times the 12. And if I put that whole thing in my calculator, so let's just show you how. So 1,000, okay, times parentheses 1 plus, and I need a parenthesis there, parenthesis, and it's 0.02 divided by 12. Okay, so 1 plus 0.02, and I can see I already have a mistake there. Let me go back. 0.02, there we go, divided by 12, and then I want that whole thing to the 20 times 12, I'm just going to multiply that out. So that's going to be 240. Whoops, 240. And I don't know why it doesn't delete if I do that. There we go. Okay, so I have $1,491.32, 33 cents. All right, and that is my answer. So that is choice 2. All right. So let's look at an actual formula that I have written here so you can refer to this. All right, so this, whoops, I meant to get a highlighter. So this is my formula. So it's a tiny bit different than the other one that I was used to. But A is going to be my amount. P is my principal or amount initially invested. Amount initially invested. R is my nominal yearly rate. T is my number of years. And N is the number of compounds per year. So we were doing this. We took the rate, we divided by the number of compounds per year. If it's monthly, I divided by 12. If it was quarterly, I divided by 4. If it was daily, I divided by 360. But then because I'm dividing that by whatever the compounds are, I also have to multiply the number of years by the number of compounds also. So don't forget this part here. The number of years gets multiplied by the number of compounds. So the rate in exercise 1 was referred to as a nominal, in name only. It's known as this because you effectively earn more than this rate if the compounding period is more than once per year. Because of this, bankers refer to the effective rate or the rate you would receive if compounded just once per year. So let's look at this. Exercise 4, I have a nominal rate of 5%. It's compounded at different frequencies. Give the effective yearly rate, accurate to 2 decimal places for each of the following compounded frequencies. So quarterly means 4 times per year. So I'm going to take that 1, and it's 5%, 0.05. I divide it by 4, but then I'm going to multiply it. The exponent will be 4. So if I was to do that in my calculator, 1 plus 0.05 divided by 4 to the 4th. So again, I have parentheses 1 plus 0.04 divided by 5. And I want to do that to the 4th power, and I get 1.0323. Wait, I did something wrong. 1.0, oh, I wrote the wrong number. Let's try it again. So 1 plus, it's 0.05 divided by 4. So I did the opposite. 0.05 divided by 4. All right, and I want that to 4th because I'm compounding it quarterly. 1.0509. So I'm going to move that decimal over. So here we go. We got 1.0509 every quarter. But I'm going to move that over 2 places. So it's really 5.09. So instead of 5%, I'm getting 5.09% per year. So you can see it's a little bit better. Same thing with monthly. 1 plus 0.05 divided by 12, because that's the number of compounding periods, and my exponent is going to be 12. I'm just trying to find out the effective rate right here. I'm not trying to do anything more than that. So again, in your calculator, you're going to have 1. Let me start with parentheses. Sorry, let's clear that. Clear parentheses 1 plus parentheses 0.05 divided by 12. Close the parentheses and to the 12th. So you can see 1.0511, I really have 5.12%. It's making a big difference, the number of compounding periods that I have. 1.05116, which is 5.12%. I'm moving that decimal over two places, 5.12%. And daily, there are 365 days in a year, so 0.05 divided by 365, and the exponent is 365. So we'll try this last one. So parentheses 1 plus 0.05 divided by 365, and to the exponent is 365. Now it's 1.051267. All right, so that is 1.05126. Bring my decimal over, 5.13%. All right, even better. All right, so you can keep on compounding on smaller and smaller frequency intervals, eventually compounding all moments of time. In our formula from exercise 3, we would be getting n as n approaches infinity. Interestingly enough, this gives rise to continuous compounding, meaning it's always being compounded, and use of the natural base e. Remember that e that we learned? This is the whole reason that we learned it, is in the famous continuous compound interest formula. So here's my formula. If I have a p principal and it's compounded continuously at every single moment, then this is my formula that I use. The principal times e, and then the exponent is r times t, and that's the yearly rate times the amount of time. So let's try a problem with that, and then we will be all done. So say a person invests $350 in a bank account that promises a nominal rate of 2% continuously. So as soon as we see that word continuously, we're going to be thinking of our formula. So I have P-E-R-T. That's 350 is my principal. E is just going to be E. My rate is 0.02, and my time is T. And that's my formula. How much would the investment be worth after 20 years? So I'm going to find 20 years. So I'm doing A of 20. So 350 times E to the 0.02 times 20. Okay, and that's going to go in my calculator. So 350 times E. My E is right here above my division sign. Times E. And then I want that to the 0.02 times 20. 0.02 times 20. Okay, and I should get 522.138, so 0.14. So $522.14. I'm compounding it continuously. Algebraically, determine the time it will take for the investment to reach $400. So I don't know the time. I know I want to make $400. So $400 equals 350 times E to the 0.02t. So I know what I want to make. So I need to solve for t. I need to solve for the time. Well, I have to get rid of the 350. I want to get that exponent by itself. So 400 divided by 350. I'm not going to do that because it's not going to go in evenly. But remember, when I have this e, instead of taking the log, I'm going to take the natural log. So the natural log of 400 divided by 350. And I'm doing the natural log of e to the 0.02t. Okay, and that 0.02 is going to come out in front. The natural log of e just cancels because it equals 1. And then to get t by itself, I'm dividing by 0.02. I'm not picking up the calculator until I have t all by itself. So this whole thing right here is going in my calculator. All right, so I have the natural log, and I'm using natural log because the natural log of e is 1, so we'll cancel out that e for me. The natural log of 400 divided by 350 divided by 0.02. So it's going to take me 6.67 years. Remember, I'm solving for that exponent. I'm solving for the time. So it's going to take me 6.67 years or 6.7 years, because it did say to round to the nearest 10th place. What is the effective annual rate for this investment? Round to the nearest hundredth. So remember, I had 350 times e to the 0.02 to the t. So I want to take that yearly multiplier, all right, and I am going to, so that's going to be 1.02, 020134. This is this 0.02 right here is this 0.02 that is right here, okay? And I'm going to subtract that from 1. Times it by 100. Effectively, I'm getting 2.02%. All right, don't worry about that one though. Let's just look at a quick multiple choice. So Akeem invests $25,000 in an account that pays 4.75% annual interest compounded continuously. How many years will it take him for his investment to triple? If he has $25,000 and he wants his investment to triple, he needs $75,000. The amount he has now is $25,000 times e to the 0.0475 t. And again, I'm solving for t. So I'm going to try and get that t by itself, try and get that exponent by itself first, and then eventually the t. And anytime I have e, I'm doing the natural log. So the natural log of e to the 0.0475 t. I'm taking the natural log of that other side. Again, I have not picked up my calculator yet. This 0.0475 comes in front. The natural log of e is just 1, so that cancels. So I'm dividing by 0.0475. So now I'm dividing by 0.0475. So I have the natural log of, where did it go? Natural log of 75,000. I guess I could have divided 75,000 divided by 25,000 is just going to be 3. So I can just do the natural log of 3, and then I'm going to divide that by 0.0475. And it's going to take me 23.1 years for his investment to triple. Okay, 23.1 years. And I know these are tricky, so let's finish up this last one. So Kristen invests $5,000 in a bank. The bank pays 6% interest compounded monthly. All right, so it's 5,000, 1 plus 0.06, but that's the yearly rate, so I'm going to have to divide that by 12 because I'm doing it monthly, and then multiply this by 12. And I want to know when her investment would double. So I don't know the time. I'm going to solve to figure out the time. What I do know is I want it to double, so I want it to equal $10,000. So I'm going to divide by 5,000. So that's going to be 2 equals 1 plus 0.06 divided by 12 to the 12t. All right. This 1 plus 0.06 divided by 12, I'm going to do that in my calculator, and it's actually going to be, 1.005. And then remember, anytime I'm trying to solve an equation where the variable is the exponent, I'm going to take the log of both sides. I'm not going to do natural log because I don't have e. I'm just going to do the log of both sides. Okay, and that's to the 12t. That 12t comes out in front. The log of 1.005. I'm going to divide by that. I'm trying to get the t by itself, so I get rid of the exponent by bringing it down in front. And then I have to divide by 12 to get t by itself. So t equals this whole thing. The log of 2 divided by the log of 1.005 divided by 12. So the log of 2 divided by the log of 1.005, and then I divide that by 12. So it's basically going to be 11.6 years.